Hello everybody, this is Mechanical Engineering by Hand, and in this video I'll talk about drag force. We covered drag force in a previous video, and the equation for drag force is the force in pounds is equal to drag coefficient times the specific weight of the fluid that the object is moving through times the area of the object and times the velocity squared divided by 2g. So let's look at an example with a car. Let's say it's going 100 miles per hour, and that equals 147 feet per second. And it's traveling through air at standard conditions. So the specific weight will be 0.075 pounds per foot cubed. And we need the kinematic viscosity. That is 16 times 10 to the negative fifth feet squared per second. Okay, and let's we need the area, so the frontal area of this car. So the area is if we're looking at the front of the car, and so let me draw what this car might look like. Let's say it's 6 feet tall and 6 feet wide, and there's a 4 square foot area here between the tires and under the car, which doesn't contribute to the area. So that area would be 36 minus 4, or 32 feet squared. And all right, now to find the drag coefficient, we need to calculate the Reynolds number. So as you probably know, Reynolds number is diameter times velocity divided by the kinematic viscosity. So that equals the diameter, I'm going to say, is 6 feet times 147 feet per second divided by 16 times 10 to the negative fifth. And that equals 5.5 million. Now we talked about how to read a log scale. There's a trick I use. If you just take the log of 5.5, that equals 0.74, and we'll use that on a drag coefficient chart. So let me show you this one. Okay, so this drag coefficient chart has the Reynolds number on the bottom, and then the drag coefficient on the left side, and then the different lines are for different shapes. And so this bottom dashed line is for spheres, and the next one up is for cylinders with a 5-to-1 ratio, meaning that they're 5 times longer than they are wide. Now a car or truck usually isn't that long. They're usually about 2 or 3 times longer. So I'm going to, and a sphere would be like a cylinder with a 1-to-1 ratio. So we have 1-to-1 and 5-to-1, but our car or truck is more like 2.5, 3-to-1. So I'm just going to take an average of those two lines right there, and that would be a drag coefficient of 0.3. Oh, and forgot to mention our Reynolds number is 5.5 million, and we took the log of 5.5, and it's 0.74. So we're going to go 74% of the way over from 1 million to 10 million. So that would be over in this area. And then we go up to that area I mentioned here between the two lines, and we have 0.3. So our drag coefficient equals 0.3. Now we have everything we need to calculate the drag force. So that'll be 0.3, 0.075, 32, and 147 squared divided by 2g, which is 64.4, and that equals 242 pounds. Okay, in a previous video we talked about horsepower, which is foot-pounds per second divided by 550. So the horsepower required to overcome this wind drag would be feet per second is 147 times the force, 242, divided by 550, and that is 65 horsepower just to overcome the force, the drag force from the air going at that velocity. All right, let's look at another example. Let's say we have a skydiver. And they're falling towards Earth. And let's say this person is 6 feet tall, an average of 1 foot wide, and they weigh 200 pounds. Okay, so let's look at our drag coefficient chart. I'm going to assume this person represents a circular disc, and I'm also going to assume that the Reynolds number is here or higher, which is a pretty safe assumption because this would be a Reynolds number of about 5,000, which is pretty low. So this drag coefficient number is steady from there on over. So that is 1.1, and so that's what I'll assume the drag coefficient is. Okay, so what we'll do is solve for the velocity. So let's see, now this skydiver is falling at their terminal velocity, which is where the drag force equals their weight, and so that drag force is going to be 200 pounds. So 200 equals the drag coefficient times the specific weight of the air, which is 0.075. We'll just say that's air at standard conditions, times the area of this person, which is 6 square feet, and then we have velocity squared divided by 2g. And so solving for velocity, we get 161 feet per second. Okay, now I will calculate the Reynolds number just to make sure that my assumption on the drag coefficient was good. So Reynolds number equals the diameter of this person, which I'm going to say is an average of the 6 and the 1, so that would be 3.5, and times our velocity, and divided by the kinematic viscosity of air. So we'll say that is 16 times 10 to the negative 5th, and that equals 3.5 million. Okay, so if we take the log of 3.5, that equals 0.54. So we'll just take a look at that drag coefficient chart. We were using this circular disc line, and we have a Reynolds number of 3.5 million, which will be between 1 million and 10 million shown here, and it'll be 54% of the way over, so about right here. And we're on the line for 1.1, so our assumption there was good. So that would be the terminal velocity of the Skydiver, and that is 110 miles per hour. Okay, thank you for watching.